Welcome to Lecture 10, in which we will continue to talk about probability. I'm going to solve a few problems during this lecture, and then, as usual, we'll have some problems at the end of the lecture. Some of you may be so familiar with probability already that you don't really need to watch the problems that I will discuss in the lecture, and so you might want to go ahead and skip directly ahead to the problems at the end of this lecture and see if you can do those. But of course, it certainly won't hurt you to look at the ones, to watch and see how I solve the ones during the lecture. And of course, even better would be to follow along with the lecture, but then before I show the solution, to try it yourself and compare to what I do. Okay, so the first problem will be 24.3.10 from your book. And for those of you who don't have the book, let me write this out for you. It says, suppose that we draw cards repeatedly and with replacement so that means we draw a card, look at it, and then put it back. Draw another card, look at it, and put it back. And just keep on doing this process. So we draw cards repeatedly and with replacement from a file of 100 cards. $50 of which refer to male. I'll just say 50 of which are male, and 50 of which are female. And so the question that we want to solve is this: what is the probability of obtaining the second female card before the third male card? Now, this is unlike any problem that we have done up to this point, and I think it's a little bit of a tricky problem, which means it's a good problem for us to think about. So, as usual, I very strongly encourage you to stop the video now and to think about this problem for a few moments, and then, try to solve it. And then when you have a solution, come back to the video and compare what you do to what we'll do here in lecture. Okay, to do this problem, I think it is most instructive. Well, actually, let me start over and say it like this. We have to understand what the problem means exactly, so let's make sure of that first. So we're picking these cards over and over. With each one, we note the gender of the card, and then we put it back and presumably shuffle the deck and then draw again. And again, then we will note the gender, put it back, and shuffle over and over. So we're asking, what is the probability of obtaining the second female card before the third male card? Okay, well, there are a number of ways in which that could be done. For instance, if the very first two cards you picked were both female, then certainly you're getting the second female before even the first male, and certainly before the third male. Or if you went female, in fact, so I'll write that down as one possibility. If we went female, female, then that's certainly one way in which you would get the second. See, this represents the first female card on the first choice, and this represents the second female card on the second choice, and so you're certainly getting your second female before your third male. So that's one possibility. And another one would be female, male, female. This would also give you your second female before the third male, or female, male, male, female. This would also work because, again, that second female here is coming before you get a third male. And we could keep on with this. There are several ways in which this could be done. And of course, what I'm doing here is along the lines of a direct calculation. Now, since and I'll put ... here, since there are a number of other ways in which we might obtain the second female before the third male. Since there are so many different ways of doing that, this is one of those situations in which you would be tempted to consider the complement and see if it's a little bit simpler. So let's think about that. Now, first of all, let's make sure we understand what the complement of this situation is. If the event that we want to calculate the probability for is that we obtain the second female, that we do obtain the second female before the third male, then the complement of that, of course, is that we do not obtain the second female before the third male. And so another way of saying that is that we get the third male before the second female. So let's say third male before second female. There are going to be several ways this can happen as well. Let's just list a few. We might have female and then male, male, male. Once we get to that third male, we don't need to go any further because that means we've gotten the third male before the second female. So female, male, 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 or male, female, male, male, or male, male, female, male, or male, male, male. But I can't think of any others besides these that would give us our third male before the second female. I'll let you look at that and think and see if you can come up with any others, but I can't think of any others right now. However, there are going to be, if we look over here at the direct calculation, there are going to be considerably more than 4 outcomes. Here's the 4 outcomes that give us the complementary situation, but they're going to be considerably more than 4 here in the direct calculation. So this is one of those situations in which it would probably be more efficient to use complements. But as a way of getting more practice, I suggest that we do both. So I'll encourage you to stop the video now and try to go ahead and complete this list here and calculate both probabilities, make sure they're the same, and then we'll look at this together. Okay, so I'll start with the direct calculation, and let's erase these dots now and try to list all the other ways in which we might obtain the second female before the third male. So we have female, female. That certainly gives us the second female, in fact, even before the first male. Female, male, female, female, male, male, female. So I believe this exhausts all the possibilities in which the first card drawn is a female. So now let's look at the possibilities where the first card drawn is a male, and then I'll assume that the second one is a female. Okay, so we could have male, female, female. That would give us our second female before our third male. Or male, female, male, female. That would also give us our second female before our third male. And what about male, male? Now, if the first two cards drawn are both males, and we want the second female to come before the third male, then we'd have to have F and F. Both of the next two would have to be female in order for the second female to be chosen before the third male. So let's see here. I can't think of any others here. I believe that this is it. I believe that these are all of the possibilities for the direct calculation. And as I mentioned earlier, these are the possibilities for the complement. And so really there's not quite as much of a difference as I had anticipated. Here we have 6 probabilities we have to calculate, and here we would have 4. And then we remember, when we calculate using complements, we take 1 minus the sum of these probabilities. So let's now verify that we get the same answer either way. So with complements, okay, well, let's calculate the probability of each one of these outcomes. The female, okay, the probability of getting female with the first card is 1/2. And then remember, we're putting that back because it says we're drawing with replacement. So we put that female back, shuffle it, and draw again. And the probability of getting female on the second one is 1/2. And so that gives us 1/4 for this probability. For the next one, the probability of getting female on the first draw is 1/2. The probability of getting male on the second one is 1/2. And the probability of getting female on the third is 1/2. And so the probability of that is 1/8. And you can quickly see how this is going to go. It'll just be 1/2 to the power equal to the number of cards we draw. So this is 1/2 squared to give 1/4. This is 1/2 cubed to give 1/8. This would be 1/2 to the 4th, so we would get 1/16 here. This would be 1/2 to the 3rd, so we get 1/8. This is another 16th, and this is 1/16. And so now if we add all those probabilities together, 1/4 is the same as 4/16, and 1/8 is the same as 2/16. And then we have 1/16, and this 1/8 is 2/16, and then 1/16 and 1/16. And so altogether, the direct calculation gives us a probability 4 and 2 is 6, 7, 8, 9, 10, 11 sixteenths. And now let's calculate this using complements. Okay, the probability of female, male, male, male is 1/2 to the 4th power. Which is 1/16. The probability here is 1/2 to the 4th power, so another 1/16. Here's 1/2 to the 4th power, so that's 1/16. And finally, this is 1/2 to the 3rd power, or 1/8. And so the probability here would be 1 minus the sum of these probabilities. 1/16 plus 1/16 plus 1/16, and of course 1/8 is 2/16, and so that's 1 minus 5/16, and so we come up with P is 11/16. So indeed we have arrived at the same answer through the direct calculation and through using complements. And that's how we could solve a problem like this, 24.3.10, which is rather different from any of the previous problems we've solved. Next, let's consider problem 24.3.12. This says, if a circuit contains 4 automatic switches and we want that with a probability of 99%, during a given time interval the switches to be all working what probability of failure per time interval can we admit for a single switch? So we have, let me just give you make sure you understand this, and then I will encourage you to try it on your own. But we have these 4 switches, and each one of them, they're considered to be identical switches, and so they all have, each one of them has the same probability of failure. And the circuit has 4 of these. So presumably the circuit will fail if even a single one of those switches fails. And we want the probability that the circuit does not fail and in a certain time interval to be 99%. So that means that the probability that not a single one of those switches will fail in this time interval is 99%. And so if that is our goal, then what is the greatest probability of failure that we could tolerate for the individual switches? And let me just point out that this probability, you know for sure that the probability of failure for a single switch has to be less than 1%. Because if a switch, let's say if each one of these had a 1% chance of failure, that means that each one would have a 99% chance of not failing. But if the probability of a single one not failing is 99%, then the probability that 1 out of 4, because there's if any one of the 4 fails, then the circuit fails. And so if the probability that that 1 works is 99%, then the probability that all 4 will work during the entire time will be less than 99%. So that would not work. That would not be acceptable. So this probability of failure, at a minimum, we can just say from common sense that it's going to have to be less than 1%. But we want to see just how large it could be. We would, obviously, if we said that probability of failure were 0, then that would satisfy this. But that's going to make these switches very, very expensive to have 0 probability of failure. So we're looking at the largest probability of failure that we could admit, because that'll presumably give us the cheapest price. So as usual, I suggest that you stop the video, think about this, try to work it on your own, and then we'll all look at it together. Okay, so let's see how we might approach this problem. So the probability, we want the probability, well, okay, let's just maybe do it this way. Let P equal, or P be the probability of failure of a single switch. Now, we want the switch not to fail, but to work during the entire time period. So let's just point out that 1 minus P is the probability that the switch does not fail. Now, there are many ways that the circuit could fail. We could have, during the time period under the time interval under consideration, we could have one switch fail. We could have the first switch fail, or the second switch fail, or the third switch fail, or the fourth switch, or the first and second, or the first and third, the second and fourth, the second and third, and so on. There's a number of different ways in which the circuit could fail. And so if we begin to look at probability of failure, we're probably going to have to calculate quite a few probabilities. But if we look at the probability that it doesn't fail, then we only have to look at one probability, because the only way that the circuit does not fail is that every single switch does not fail. So let's think about that. Probability that the circuit does not fail. Okay, probability that the circuit does not fail. Well, we already know that we want that to be 99%. But let's think now in terms of this variable p that we've introduced. Let's see how the probability that the circuit does not fail is related to p. Well, as we just said, the only way that the circuit will not fail will be if the first switch does not fail, and the second switch does not fail, and the third switch does not fail, and the fourth switch does not fail. So the probability then that the first switch does not fail is 1 minus p, and probability that the second will not fail is 1 minus p. The probability that the third does not fail is 1 minus p, and the probability that the fourth will not fail is 1 minus p. So we have the equation that 1 minus p to the fourth power is equal to 0.99. So 1 minus p is equal to 0.99 to the 1/4 power, and therefore p is equal to 1 minus 0.99 to the 1/4 power, and therefore p, let's give me just a moment to calculate this. I get that p is equal to 0.0025. This is the value. This is not the exact value, but that is the value to 4 decimal places. Or in other words, 0.25%. So each of these 4 switches would have to have a probability of failure of at most 0.25% for us on average to have a 99% probability that the circuit will not fail. Okay, and that concludes problem 24.3.12. And now let's do one more problem before looking at the problems that you'll work on. So for the last one, let's look at 24.3.14. And it says, I'm going to modify this just a little bit. Well, in the production, well, let me just go ahead, maybe just copy it directly. Suppose that in a production of spark plugs, the fraction of defective plugs has been constant at 2% over a long time. And that this process is controlled every half hour by drawing and inspecting two just produced. Find the probability of getting A, no defectives, B, one defective, C, two defectives, and then there's one more question. What is the sum of these probabilities? Now, actually, I hope you realize already this problem is much easier than the other two that we've considered, and so I hope you'll have no problem with it. But again, please stop the video now and try to answer all four parts of this problem. By the way, I hope that you can already answer the last question, the one that says, what is the sum of these probabilities? I hope you can already answer that, even without calculating anything about A, B, or C. But try to do this problem, and then we will work it together. Okay. So the fraction of defective plugs has been constant for, and is equal to 2%. And so if that's the probability of getting a defective plug, and we inspect two plugs, what is the probability of getting no defectives? So for A, well, the only way in which we can get no defectives is if both the first plug drawn and also the second plug drawn are both not defective. Now, if the probability that both of them, if the probability that a single plug is defective is 2%, then the probability that it's not defective is 98%. So the probability that the first one is not defective is 0.98, and the probability that the second one is not defective is also 0.98. And so the overall probability we get for A will be 0.9604. Now for B, we want to know the probability of getting one defective. And there are two ways in which we might get one defective. We might The first one might be defective, and then the second one is not defective, or we might get the first one is non-defective and the second one is defective. So we have to include both of those here. So the probability that the first one is defective is 0.02, and then that the last one would not be defective would be 0.98. But then another way it could happen would be if the first one is not defective, which is 0.98, and then the second one would be defective, so 0.02. And so when we calculate this, what do we get? I'm getting 0.0392 for this probability in B. And now for C, what is the probability that both are defective? Well, there's only one way in which that could happen, and that would be if, of course, both are defective. And so we have 0.02 is the probability that the first is defective, 0.02 is the probability that the second is defective, and so 0.0004 is the probability that we get in C. And then for the total of these, we have 0.9604 plus 0.0392 plus 0.0004. And let me make sure this does come out to what it should be. And indeed, it comes out to be 1. Now, I hinted before that I hope that you would be able to find that total or know the total even before you calculated these individual probabilities. Now, why did I suspect that? Well, it's because no defectives or one defective or two defectives, those are the only possibilities. Those are the only things that can happen if you pick two spark plugs. And so when we look at all possibilities and add up the probabilities of all of those, we must obtain 1. And in fact, that's how the method of calculating by complements works, because if you consider all the possibilities, then the probabilities of all those added up will always equal 1. So, as I said, this is actually the easiest problem of the 3 that we've solved in the lecture. So now, let's identify some problems for you to work for next time. Okay, so the first problem for you to work, 10-1, and this is related to problem 24.3.13 in your text. It says a pressure control apparatus contains 3 electronic tubes. The apparatus will not work unless all tubes are operative. If the probability of failure of each tube during some interval of time is 0.04, what is the corresponding probability of failure of the apparatus? And the answer here is exact, whichever one is correct. It is exactly correct. And the choices are A, 0.000064, B, 0.12, C, 0.115264, or D, 0.04. And for the second problem, this one is related to 24.3.15 in your book. Suppose that if you fire a single shot at a target, the probability that you will hit it is 1/8. If you fire 4 shots, what is the probability that you will hit it at least once? And the choice, again, the answer here is exactly correct. Choice A is 1/2. Choice B is 1/8 to the 4th power. Choice C is 1 minus 7/8 to the 4th power, and D is 7/8 to the 4th power. And then, as usual, there will be at least one additional problem, possibly more, in class. So that's it. That concludes lecture B10, and good luck.